In this video, we're going to review analog circuit noise. We're going to go fairly quickly, assuming you already have some background in this area. And if it's a little too quick for you, there's lots of great resources and books that can help you get back up to speed. Resistors contribute noise in analog circuits. Specifically, they contribute thermal noise that can be modeled by a voltage source connected in series with each resistor R. Now, the voltage source, since it's a noisy voltage source, we can't say precisely what its waveform will look like as a function of t, but we do know something about its statistics. Since it's thermal noise, it has a white power spectral density, and its power spectral density is given by 4 kTr, where K is Boltzmann's constant, T is absolute temperature, and R is the value of the resistance. So again, that's the power spectral density of that voltage noise source. We can also develop an equivalent model simply by taking the Norton equivalent here. And we do so by just, in the usual way, by saying that this equivalent noise current is equal to the noise voltage Vn divided by R. In fact, it should be Vn over R here. So we can just square both sides of that expression, giving rise to the relationship shown here. And therefore, the power spectral density of the Norton equivalent noise current source is, instead of 4 kT times R, becomes 4 kT divided by R. MOSFETs modeled in their active region, or saturation, also exhibit thermal noise. That is, the drain current that we expect to flow through the MOSFET purely as a function of VGS, in fact, exhibits thermal variations. And so that can be modeled by adding a small noise current source in parallel with a noise-free MOSFET model. So these, this noise source here captures the variations in drain current when the MOSFET's in the active region. And so it can have either polarity, of course, since it's a random signal. We don't know its precise waveform, but again, we know something about its statistics. It's thermal noise, so it's spectrally white, and its power spectral density is given by 4 kT times a technology-dependent parameter, which is equal to 2/3 for long channel devices and in older technologies, but in general may be larger. And all that times the transconductance, small signal transconductance, GM of the transistor. For more advanced technologies or short channel lengths, we would replace this constant 2/3 with a parameter gamma. And in fact, at very short channel lengths, values as high as gamma equals 2, or actually even more, have been reported. So this model for the thermal noise of a MOSFET, where the drain thermal noise current power spectral density is given by 4 kT gamma times GM, suggests that for lower noise, we might prefer a smaller value of GM in the transistor. But this depends on how the transistor is being used. If the transistor, for example, is being used in a common source configuration where really what it's doing is amplifying a small signal gate source voltage, then the situation is a little different, because if we try and improve the noise performance by decreasing GM, well, we're also giving rise to a smaller current signal at the output, GM times VGS. And so, sure, we might have less noise at the output, but we've also got less signal. And probably what we really care about is signal to noise ratio. So in such cases, it's useful to think about the gate-preferred thermal noise of the transistor. So that is, what noisy voltage VGS would be required to give rise to the same amount of thermal noise current at the drain of the transistor. And so we can find that simply by taking ID and dividing it by GM. Now, if we're talking about the power spectral density of the thermal noise drain current, then it has units of amps squared per hertz, and so we should divide by GM squared to get the power spectral density of the voltage noise source, VI squared. So writing the expression for VI, now we see that the small signal transconductance of the transistors in the denominator, so that clearly emphasizes that in terms of the input referred noise that we would see appearing directly superimposed on our small signal VGS, then we would, in terms of that, we would like to actually increase GM, and that would in fact give rise to a larger signal to noise ratio. So a couple of caveats here. Again, this is the case for transistors that are being used to amplify a VGS, right? So that, even so, a larger GM will still give rise to more noise current at the output, but it will um, give rise to an even larger signal current. And so the improvement in signal current outstrips the increase in noise current. So it's a net benefit in those cases. But if the transistor is just being used to provide a DC bias, then the extra noise current is just purely extra noise. So for transistors that are just being used not for us not to produce a signal current, but just to produce a DC bias current, then indeed we would prefer a smaller value of GM in general to give us less noise running around the circuit. Second caveat here is that this equivalence is not really strict. Because, for example, in an extreme case such as the one pictured here, if there's no, if the gate is left open circuited, for example, then you can have whatever noise voltage you want arising in this fictitious source. It's not going to modulate VGS at all of this transistor, so it's not going to give rise to any change in drain current. So that just illustrates that, this equivalence relies on the fact that, you would get a proper equivalence if this were grounded, small signal grounded. But in other cases where if the impedance connected there is large, then it's not a strict equivalence. And then just the final thing to keep in mind here is that not to imagine that there is, by looking at this model, not to imagine that there is actually a noisy voltage that can be observed at the gate of the MOSFET. That's simply not true. This is just a model that captures the thermal noise that tries to emulate the thermal noise that actually arises in the drain current. In fact, physically, there's no variation in gate voltage at all observed. There's only variations in drain current that are observed due to thermal noise in the MOSFET. An additional source of noise in MOSFETs is often referred to as 1 over F noise. It can also be called flicker noise or pink noise. It's different than thermal noise. Actually, its deep origins are not fully understood as far as I can tell, but generally it's thought to arise because as current flows along the semiconductor surface of the channel region, just under the gate oxide, there's going to be surface imperfections there that cause charges traveling down the channel to occasionally get trapped, and once trapped, they may get released. And the frequency with which this occurs it's governed by a certain stochastic law that ends up showing up as uh, a noisy process with a power spectral density proportional to 1 over F. So the way we model this noise source is including a noisy voltage source in series with the gate whose power spectral density is given by K. This is an uppercase K. not Boltzmann's constant. It's purely a flicker noise constant that is again technology dependent and in general will be different for the NMOS and PMOS transistors in a given technology. In fact, it's generally lower for PMOS devices and is just something that in practice is really empirically determined by fabricating MOSFETs and measuring their 1/f noise. So that's a kind of proportionality constant in the numerator. And then the other dependencies are that flicker noise is inversely proportional to the gate area, W times L. So you can think of this as just arising because if you have a larger gate area, you've kind of got a larger surface area for the channel. So these random events where charge carriers are getting trapped and released kind of get averaged over a larger gate area. So it looks like less 1/f noise. So for less 1/f noise, you want a very large device. You could increase both W and L to see that. And then there's also the denominator Cox, and of course there's the 1/f term. So, it's interesting that this 1/f noise obviously gets very, very large near DC, and the way to reduce it is to make the gate area really, really large. So this can be thought of as being similar in a sense to random offset. Random offset is also something that predominates at DC, obviously. And the way we minimize offset due to mismatch is to make the transistors have a large area, W times L. Um, so, and this in a sense is convenient because if we have an amplifier whose DC performance we really, really care about, that is, we're using it mostly for very low frequency or DC signals, then we might not mind using large transistors. The associated parasitic capacitances presumably may not cause us too much trouble if we're dealing with very low frequency signals. So shown here on the right is the complete MOSFET noise model with the 1/f noise term in the gate and thermal noise current modeled here with this current source ID and a white power spectral density. Let's finish off by just going through an example noise analysis. In this case, we've got a common source amplifier where the NMOS transistor Q1 is the common source transistor, and the load is PMOS transistor Q2 with the gate connected to ground, keeping Q2 in triode. So it presents a load RDS2 for Q2 in triode to the common source transistor. Let's also assume that there's an output capacitance CO between Vout and ground. And we know that the small signal output resistance here is RDS1 in parallel with RDS2. Now, when we're doing noise analysis in general, we can certainly perform small signal analysis since all of these noise signal sources are small enough to validate our small signal linearized approximations. And the way we need to do small signal analysis to consider each noise source in turn and then sum their effect at the output. So the noise sources of interest here are the thermal noise of Q1. We may be interested in the flicker noise of Q1. There's also thermal noise of Q2. Q2 doesn't have flicker noise because it's not in active mode. It's in triode. It's essentially just a resistive channel region with a resistance of RDS, and so therefore has the same noise model as a resistor with a value of RDS. First, let's consider the output noise due to the thermal noise of transistor Q2. So if we want to simplify a small signal model for this, we've got the thermal noise current of Q2 here, and that is over here. It's seeing a small signal ground at one end, and the other node is Vout, to which we see connected small signal Rout. Remember that's RDS1 in parallel with RDS2, and the output capacitance CO. So if we can't compute a deterministic waveform at V out, but we can compute a power spectral density. V out would be given by the power spectral density of the noise current source ID2 through the single time constant low pass filter formed by R out and CO, and with a DC gain of R out. So here is that frequency response squared, right? So the DC gain of this term here is obviously R out squared, and we've got the pole, the single time constant pole arising at a frequency 1 over R out CO. So this then is the power spectral density of the noise at the output, noise voltage at the output. We're calling that VNO2 because we're only so far considering the thermal noise of Q2. Now we can find its total RMS value by integrating this expression over all frequencies. And if you do so, you get the expression shown here. KTR out over RDS CO. Now you can do a very similar analysis now for the thermal noise current of Q1. In this case, you should neglect all other noise sources and just perform the analysis for ID1. But of course, the analysis looks very, very similar because it's a current source connected to the output node, the other end connected to ground. The only difference is that the power spectral density of ID1 is a little different because Q1 is in active mode, whereas Q2 is in triode. And so that would give rise to this expression here. Main difference here is that you see the term GM, that's GM1 showing up because, again, the thermal noise of a transistor in active mode, GM1, is proportional to GM1. Whereas for Q2, we've got the term 1 over RDS2 instead because it's in triode. Next, we may consider the output noise due to the flicker noise of Q1 by introducing our flicker noise current source here. Okay, and then that gives rise to a noisy current spectral density equal to GM1 squared times VG squared F, and then that current then flows in parallel combination of R out and CO. So here is the flicker noise VG squared power spectral density, and here it is multiplied by GM1 squared, and then that again sees this single time constant first order filter at the output with DC gain R out squared, and then the single time constant response with the pole at 1 over R out CO. So again, the total noise at the output would be the superposition of these three. The noise at the output, spectral density. You've got the noise due to the 1 over F noise corner here. Then you would also have the term due to ID1, and that's going to be a low pass filtered one. And then you've all got a similar looking one due to the thermal noise of Q2, and that may be more or less than that due to Q1, but with the same, they've all got the same corner frequency determined by the single time constant at the output. But you can see from this sketch that the 1 over F noise shown here in red is most likely insignificant unless the amplifier bandwidth, this corner frequency, is low enough that it's comparable to this crossover point here. Okay, and that crossover point depends solely on the properties of Q1 because that's the point at which this noisy drain current due to the 1/f noise has its, the frequency at which its power spectral density is exactly equal to the white power spectral density of the thermal noise drain current. So that equating the two power spectral densities and solving for this frequency here, called the 1/f corner frequency of Q1, gives an expression like this. And that's typically a fairly low frequency for, especially for older technologies, although that 1/f corner can start getting high in more advanced technologies. So the bottom line is that the flicker noise term is only going to be significant if we're talking about an amplifier with a relatively low bandwidth, comparable to the 1/f corner frequencies of the transistors at play here. If it's a broadband amplifier, then the thermal noise terms, the blue and the green ones, will predominate. So finally, to get the output noise of this circuit, we can superimpose all the noise contributors. We can just find the total output RMS noise by adding together the RMS noise of the output due to each of the three noise sources. And here we're just assuming that it's a fairly broadband amplifier, so we're neglecting the 1/f noise of Q1. So we've got the thermal noise of Q1 that gives rise to the gamma dependent term here. And then we've got the thermal noise of the resistor RDS2 formed by Q2 and triode. And so that gives rise to this term here. So you'll notice that the contribution of Q2's thermal noise does not depend on GM1 because we've got, with this term here has GM1 in the numerator and the denominator, and then there's GM1 in the numerator showing up here. So in all these expressions, GM is just GM1. Whereas the thermal noise at the output due to Q1 is proportional, its power spectral density is proportional to GM1. So writing the expression out in this way just highlights that the term due to Q1, which shows up as gamma there, is very likely to be larger than the term due to Q2 thermal noise. Because the blue term in the brackets there is 1 over the gain of the amplifier, 1 over GM1 times RDS2. Whereas the green term is something like 2/3 or larger. So as long as there's any reasonable gain in this amplifier, it's certainly likely that the green term will dominate. And so overall, the noise at the output of this amplifier is likely dominated by Q1. Specifically, it's thermal noise, as long as the amplifier has a bandwidth greater than the 1/f corner frequency of Q1.